Yes. So it's a 2-week summer school, right? So really, if you wanted beer, you should have asked on day one, can we get some malt and some grain? And you would have actually got beer the second week. So anyway, keep it in mind for next time. Yeah, so I got a couple of slides that I'm going to start with before going into the more interactive part. For those of you who are not familiar with software development as much, if you want to use the time while I'm going through the slides to low-key kind of get a GitHub account, that will be useful. If you have a GitHub account, you're all set. That's all you're going to need for the tutorial. So GitHub, GitHub, in case anyone's not familiar with that. So I'm going to talk a little bit about sort of what we're trying to do differently with software at EIC. Some of you may be familiar with that. Who has used any kind of EIC related software over the past, let's say, year? Okay, fewer than I had expected, but that's good. Then that means everyone's going to learn a lot. So what we're trying to do with the software that's different is dealing with the fact that EIC is bigger than the past. We've had big experiments in the past in nuclear physics, STAR, Phoenix, S-Phoenix now, GlueX, but EIC as a community is larger than that, and it requires that we do things a little bit differently than the nuclear physics community has been used to. And I'm going to talk about nuclear physics as sort of the, in contrast to the high energy physics community, which already has experience with these sort of order 1,000 people collaborations. We're getting into that area now with the EIC. So that means things are going to change for how we do software. The other thing that's different is that EIC is going to use a fundamentally different way of taking data. It's going to use what is called streaming readout. So the data is coming in all the time. It's not triggered. It has to be analyzed as one data stream while it's coming in. So again, that means that software becomes more important. And then finally, the other big difference is that EIC is going to be, I would say it's the first large international facility that the DOE is really building. It's from the ground up international. I'm standing here as someone who's from Canada, well, not originally, but now there at least. There's fundamental involvement from Europe, from India, from Japan, and that is also affecting the software. So whereas the LHC is used to that and has the WLCG, the worldwide LHC computing grid, we are going to need something similar as well for EIC. So it's going to be a distributed computing environment. So what's the easiest way to tell someone just going to pick a country in Italy to contribute as a funding agency? It's to allow them to contribute resources they already have, which is usually a large computing center. So to be able to do that, we have to make sure it's easy for those people to contribute. It's easy to build a community that's writing software that allows the users in Italy to participate in EIC science through their CNAF computing facility, similar to how someone at JLab wants to contribute through their JLab computing account, and someone at BNL would want to contribute through their BNL account. We're also thinking about this in terms of openness of data. Already now, we don't have data, we have simulations, but we're thinking about how do we make sure from the start that things are accessible, are openly available, and can be easily analyzed even without having, a memorandum of understanding or as it's called nowadays, non-proprietary use agreement with one of the labs or with the Department of Energy, so that someone at a university that doesn't have a pre-existing connection with EIC can actually access these resources. And then finally, what we're trying to do is make sure that while you, as young scientists who may not necessarily want to spend your entire life as a scientist, but are currently scientists training for potentially a position in industry, how can we help you be, how can we help you gain the skills that you need for that transition to industry? It doesn't, for those of you who are experts at root, I'm going to disappoint you by saying that root skills are not necessarily all that desirable in industry. They're not a bad thing, don't get me wrong. But for example, if you compare it with Python, people are going to know what Python means, and they're going to think that that's useful. So the other part of this all over the past couple of years is that we've used sort of a design framework to come up with these software tools and to put the pieces together and to look at the community and help us figure out what is necessary. And that's called user-centered design. So the user is the user of the software as opposed to the developer. Some developers are going to be users as well. Ideally, we want all developers to be users as well. But the users are more than what plays a role in the design of the software and the design of the computing environment is more than just the developers. It's written for the user, it's written for you. So we are interested in figuring out what is important to you as users. That's why I have my notepad here. It's not to keep my notes, it's to write down what you're all going to say as comments, because you're part of this user-centered design. You're the users in user-centered design. So we want to gain understanding of those users, communicate that to developers, and then implement better solutions, particular solutions that are going to be adopted by users and be seen as a benefit for users. So we have gone through an intentional decision selection process for all of the software components that we have in our environment, including some of the hardware infrastructure that we're currently going through. There's big data centers that have to be built to support some of EIC, in particular abroad, that requires that there's even middleware and backend server software that needs to be decided upon. But in the end, that has to start from what is going to help us in user-centered design. That's sort of the gist of my talk. Now I'm going to go a little bit more detail through that. As I think it was Chiprin who pointed out, obviously there's lots of people's input in all of these slides, and unfortunately this gets cut off a little bit there, but there's names at the bottom of people who have contributed significantly, in particular to the user-centered design aspects. All this, EIC, so what's new? Large luminosity, so that's going to affect the software in particular. Polarization, that doesn't necessarily affect the software as well. The international community is affecting the software, so that's going to be the two things to highlight here. Back in 2016, we started this as a consortium, sort of just a merry band of people together writing software and trying to figure out how to make things talk to each other. Common interfaces was the main thing. So one of the things you'll see with software is that a lot of the individual pieces might work well, but they don't talk well to each other, and that is where the friction lies. Oh, there they are. I should move that too, so you can see the funding agency. So we are working primarily at that time on interfaces, including, for example, what's a good way of making it possible for people to exchange data with each other. Some of you are familiar, and maybe it has already been mentioned. Well, I can use as an example something that just came up in the previous talk. LHA PDF. LHA PDF works because it provides one standard interface to a lot of different PDFs. You learn that interface, you can use any of those PDFs. So that's what we're trying to do, or what we were trying to do at that time, is figuring out what are the interfaces that EIC data, EIC software has to follow. or should follow. And then everyone who uses those interfaces can have their software talk to each other. So it first started as a software consortium, just a loosely affiliated group of people. Then we were able to integrate it in the EIC user group as a software working group. Gives it more coordination power and so on. We were able to significantly impact the yellow report preparation. Who's familiar with the yellow report? Okay, yeah. So the yellow report is sort of the overview of what is the physics that is going to come out of the EIC and what are the detector technologies that are going to make that possible. It's not a detector design, but it's sort of a comprehensive overview. Lots of detector studies went into that. Then we also were able to contribute to the detector proposal development, which of course relied on a lot of software. And then since then, since about a year ago, a little over a year ago, we have the EPIC collaboration. So the computing and software working groups, or working group now, are continuing this work, not in service only of EPIC though. The goal here, I say this specifically, Bill, this is not just for EPIC, this is for all detectors, also second detectors. So we are not writing software just for a single detector, but we're trying to make sure that we can even exchange parts and pieces with other detectors, with other accelerators, with developers outside of the EIC community. So yeah, we went through this single software stack decision process. Now people might ask, why a single software stack? What were there two? Yes, there were two software stacks, of course. There were two proposals that were competing, and that led to EPIC. And so the single software stack decision process was sort of taking what we learned from both of those proposals and taking the best pieces and figuring out what worked well, putting that together into the current software environment. Now, one of the things that's somewhat challenging with the EIC, not just somewhat challenging, but very challenging, is that we're writing software now that is going to have to be used for data taking for analysis in 2035. Think back 10, 15 years ago, what software looked like back then, and it looks very different than it looks now. 10, 15 years ago, people using Python were a very small minority. Now, this is, of course, very different. That also means that in 10, 15 years from now, we might all be writing Julia, not Python. We might all be, we will have GitHub Copilot program everything for us. So we have to allow for that kind of evolution. And our argument has been that by focusing on interfaces, we allow for the flexibility to experiment with individual pieces. And it only works if those pieces are small. They can be swapped out with another piece instead of it. And so we encourage this modularity with well-defined interfaces between the modules. Now back to the computing side, there's two host labs, BNL and Jefferson Lab. It's an international facility. There's going to be people and labs from around the world that are contributing. There's an EIC Resource Review Board, RRB, that's already working on integrating these international partners through distributed computing. So we want to be able to send computing jobs to those sites all around the world. This has been done in the past. So GlueX, SPhoenix are using the Open Science Grid, which is sort of the LHC, WLCG grid, but then for open science, for not just LHC science. So that's been a standard that's evolved here in the US, primarily through DOE and NSF, and that we're focusing on as a starting point for this. The other part of this distributed computing model is that we're going to streaming readout. So we don't want to have runs that we then have to, reanalyze or reprocess, but we want to have essentially everything flow through to rapid turnaround time with results. So that means that, for example, data that gets taken here, here on Long Island, is streamed right through to, for example, an Italian, continue with the example, it's going to an Italian data processing site, and then maybe some of the data is stored there, it's stored in duplicate, maybe at Jefferson Lab. So everything's kind of distributed across the world in a way that is not too different from what LHC is already doing, but more so, and with streaming readout. All of this is also happening now in the era of artificial intelligence, machine learning. So we want to take this large data volume and be able to analyze it with artificial intelligence methods. One of the things that helps us there is, again, focusing on interfaces, making sure that it is that the data is in shapes, in structures that are easy to analyze for current machine learning models or current machine learning environments. So we've got our two wings to the data model here. We've got Brookhaven, we've got Jefferson Lab. There's already existing universities that have affiliations with either of those. So we don't want to break those affiliations. People who have an affiliation with Jefferson Lab, if you have a Jefferson Lab account, who has a Jefferson Lab account? Some of you have a Jefferson Lab account. You should be able to use that to access computing facilities. Who has a BNL account? If people have BNL accounts, should be able to use their BNL account to access EIC facilities. But then people at other facilities should be able to do that as well. They're in this echelon 2. These facilities, that's, for example, then the CNAF in Italy. It's leadership computing facilities, HPC sites, large GPU processing centers that are focusing on machine learning. So those are all integrated in that model as well. And so data gets taken at the experiment, gets flowed through Jefferson Lab, analyzed here, flows back to BNL, or gets stored in some kind of distributed way across these sites. Now that's different. It's different from how nuclear physics has been doing this in the past. It's closer to high energy physics, but it's also a little bit different from high energy physics. And this gets back to sort of culture change and the reason why culture change is hard. Culture is one definition from organizational psychology is culture is the way we do things around here. The vague definition, but it's one that works. It's, you know, if you think of your university or of your research lab, it has a culture, and that's the way you do things in your research lab. If you start every group meeting with, I don't know, going around the table once and letting everyone give input, that says something about the culture in that research group. If the first thing that happens is that the PI stand up and gives a 30-minute lecture, then that also says something about the culture. None of these are bad. It's just that's the way we do things around here. So in nuclear physics, we've been doing things differently than what we need for EIC. It means that our software and computing systems are going to have to change to accommodate for that, and we're going to have to change that culture a little bit. So we're going to have to deal with these larger, more complex computing systems, things that talk to each other, things that are at the interface are more structured, where you can't just say, well, I'm gonna add this new data field because I need it. It's gonna maybe need a little bit more discussion. So that means we have to come up with some of the structures around that. So one of the things we're currently working in, and which many of the people in the EPIC collaboration may be familiar with already, is sort of more modern code management practices. So we're a collaboration, so we look at coding also as something that happens collaboratively. It's where people are engaged with each other. You don't just go off and write some code and then half a year later come back and tell people, here's, I've solved it for you. No, there's a lot more interaction between people during the process of writing code to make sure that it is owned by the collaboration, that there's not just one person who's an expert. We go through what are called code reviews. So I go through code reviews. I have all my code written that I write. It gets reviewed by someone else to make sure I don't make any stupid mistakes. To make sure that all my stupid mistakes are caught, because everyone makes mistakes. And that's a little bit of a change in how people are used to handling this in nuclear physics. And of course, there's different users who adapt to this differently. So there's maybe not as I will say that students are generally well in understanding of code, having to go through code review. Professors are not necessarily always as used to having their work reviewed in that way, which leads to sometimes a little bit of friction. But this is how EIC is sort of affecting the software development process in nuclear physics. Now, because this affects various users in different ways, we use this user-centered design. So it's a multi-stage problem-solving process that requires that we analyze what the users are doing, and then also test, validate that what we think the users are doing is actually correct, and use that in our design. So we've got our long-term researchers who might have been in the field for 10, 15 years. Those are the ones that are sometimes hard to change. They're often too busy to learn a new language. So if we say we're going to do everything in Julia, then I'm just using Julia as an example, just like I'm using Italy as an example. None of those should be taken as being a direction where we're going to focus in exclusively. That's not it. But someone who's used to writing things in C++ and has done that for 15, 20 years might not want to change to a different programming language. Could even be Python. Short-term researchers, some of you may be among these short-term researchers. You're probably more familiar with some of the more modern languages. You might not have grown up with Fortran. Or maybe there's a sufficient number of, dare I say it, theorists here who have still models that are strongly written in Fortran. So you may be looking at different things. You're motivated to learn new skills because maybe you're thinking of transferring that to a different industry or different field. So we look at users in the EIC. We do this annual state of the EIC software exercise. It's a survey that we repeat every year. Same question, so we can compare year over year, and we look at what people are using, which environments, where are they doing their computing. It's not a very long survey. It's, I think, 15 questions or so. So we get a fair number of responses, and we can see what is it that people are using for detector simulation. So root, Jan4, EIC smear, fun for all, and so on. And we see things get smaller and smaller. DD4HEP is probably in the latest, if we were to do the survey right now, DD4HEP would be probably up here at over 50%, because that's one of the tools that we're using now. What are physics event generators? It depends a little bit on what time you ask this question, not what time of day, but in a time when there's more focus on detector studies, it was more Jan4. Once we get to more studies of physics processes, we end up seeing PCN and DIS event generators. Yep.
How many people normally fill this out?
I think we got somewhere. Yeah. So here, the 61, 54. So not everyone fills out every question, and some people fill out multiple answers. So, but that's about the order of magnitude. People who fill it out. We wish this was, of course, larger, but it will go up as the community gets larger. In terms of a return, this is actually not so bad for a survey that doesn't have any incentives associated with it. This is a starting point. These quantitative surveys, so that gives us numerical information, of course, subject to some bias of selection. But it allows us to pick then a couple of people that we are interested in drilling down in specific topics. Some of you might have participated in these focus groups, where we really ask, what is it that you would want in EIC software? What is it that you're doing? What are you working on? Tell us how your day is scheduled. What are you waiting on when you're doing software? What do you think should go faster? What programming languages, what tools are you using? And we're using those kind of experience and those focus groups to form sort of artificial personas. They're a term, again, from organizational psychology and advertising, actually. They're almost like archetypes. Marcus Diefenthaler, he likes to call it archetypes, sort of Jungian psychology. But they're not as deep in your id. They're sort of, they're a tool that we use to say, well, in the EIC user community, we have people who are what we call software emperors, who have their little domain of software that they rule over. Now we have people who do software because they have to, not because they want to. So we have about 5 different personas that we kind of associate with different users. People might fall into multiple personas at the same time. They might be a single persona. They might change during the course of their career. But what it allows us to do is then go to the developers and say, well, how are we helping that group of users with what you've put into place? Because you forced everyone to do X, and this group really isn't going to like that because they hate writing software. So how are we going to help those users? The other thing that's nice in these profiles is that it allows us to, these personas is or the focus groups rather, is it gives us a lot of input for sort of public profiles. So these are not personas. These are actual people, but it's based on the same focus groups to some extent. What we came up with based on this input, focus groups, and user surveys is a set of EIC software statement of principles. So these are the principles that we really think are important about software, and that we are going to, that we're going to look at when we develop software practices. And this is sort of our constitution for those of you who are from the US and for others who are from countries where there's a similar type of law. So this is what's in our genes. We have, we want software to be diverse. I'm just going to read these 8 words. They kind of correspond with the 8 items over there. But there's more detail in the detailed text. So we want software to be diverse. We want everyone to feel at home in software and computing. We want it to be integrative. So we want it to integrate multiple parts of what is software and computing. We want it to be heterogeneous. So we want it to combine GPUs, regular CPUs, FPGAs, different kind of computing paradigms, future computing paradigms that we don't actually know about yet. We want it to be user-centered, just went over that, so that shall be no surprise. We want it to be accessible, which means it's open to everyone to be able to analyze and to participate in. We want it to be reproducible, so we want to make sure that 10 years from now, we can still figure out why we made a design decision based on a simulation that we run now, right now. We want it to be collaborative. It's, we have to talk to each other. We have to work together. We can help people learn and write these software. And we want it to be agile. And with agile, we mean that it's not something we're going to deliver 5 years from now. We want it to be ready now and get better and better and better over time while it is being used. The last one is a little bit of a cop-out because I'm going to show you software that is not ready in the traditional sense that it doesn't have all the bells and whistles, but it has enough bells and whistles to get started and it will get better over time. We have sort of a user-centered design mental model behind it, how everything sort of influences each other. So we start from user-centered design, sort of the aspects I talked about. That sort of influences discoverable software. We want people to not actually have to come to tutorials. Tutorials are not an effective way of learning things. Well, they're an effective way of learning things. They're not an effective way for everyone in the community to learn things. I don't know if anyone has ever done the math. I did the math last year. Everyone who came to this workshop has added 5% to their global carbon footprint this year. So sending everyone to a tutorial just for learning software is not necessarily the best solution. So we want software to be something that you can sort of learn while you're using it. You know, I have my cell phone here. I don't need to attend a tutorial to use my cell phone. Now, of course, it's different what I'm trying to do with my cell phone compared to what I'm trying to do when I get a bunch of hits out of a tracking detector. But the point is that you shouldn't have to attend a tutorial. Also, this is something that comes back from the more senior members in our collaboration. They're just plainly telling us, I am busy. I have 5 minutes to learn how to use your software. Don't let me sit through a 3-hour recording on YouTube. So it should be discoverable. User-centered design also defines what the workflows are that we want to support. So how do you do an analysis? What are sort of the different steps in there? You start with event generation, simulation, digitization, reconstruction, and analysis. But can we provide some templates that help people get started with that? So that's where we're working on template repositories, and you'll see in some sense some of that today. And it informs what kind of workflow management services we use. Someone was in CMS here, right? So you are, okay. So you're probably familiar with submitting jobs to the WLCG. That's a certain workflow. You define how your analysis is going to run on the WLCG, and then it goes out and runs there. So that's something that in nuclear physics we don't really have as a similar paradigm, and that we need to develop based on some of the user input. And all of that, in particular, once we get people to use software in a way that it is designed for, based on user input, we have workflows that we know are supported. That helps us with really the thing that's hardest for our community, data analysis preservation. So whatever you're doing now, it's important. It's important enough that no one wants to lose the work that you're doing now. It needs to be archived. It needs to be accessible for someone to look at 5 years from now. Maybe the person who is taking over the project after you move to a different position. Maybe it's, again, why did we make that design decision 10 years ago? So we need to preserve what we're doing. It can't just live on someone's laptop that now doesn't boot up anymore because the battery is dead or something like that, right? So we want to be able to have everything stored and accessible later on. That helps if we can support certain workflows and support certain discoverable software practices. All that a little bit new to nuclear physics. So how does our software stack look like, and what is it trying to do? Well, what it's trying to do, I just explained. But this is sort of the components we have decided on through sort of a community input decision process. So we're primarily focusing on this chunk here, the chunk between the event generators and the ultimate physics analysis. There's too much variability in the physics analyses for us to really be able to define that and provide tools to support that. There's also too much variability in Monte Carlo event generators, and frankly, we don't know enough physics to write them. We leave that to the experts. But you can see there's an interface here. There's an interface here. So Monte Carlo event generators will produce something, and we expect a standard format. It's HEP-MC3, high energy physics Monte Carlo standard, 3rd version. Which is used for storing Monte Carlo event generator output. If you are developing Monte Carlo event generators, writing HepMC tree output is going to make it 100 times easier for someone to analyze it in the context of EIC. We run detector simulations in Jan4. That's pretty much a standard for full simulations. Fast simulations, we also want to run in Jan4. Those are approximating simulations where we don't do the full tracking of particles in electromagnetic showers. That's something that is currently in progress, but the main thing there is we don't want to use a different tool for that. We have a readout simulation, which is what we call digitization. That's where we say, well, what does one hit in Jan4 correspond to in the real world? One thing that I mentioned is we're using streaming readout. So instead of having triggers where we can say this is the detectors that had hits, we don't actually have that. We get samples, and we get pulses that are sampled maybe 5 times. We get 5 pulses, 5 samples for 1 pulse. We have to simulate that. So that's a readout simulation or digitization simulation. We're reconstructing these events based on that readout information, digitized information, and we're reconstructing in a framework that is developed to deal with these streaming readout environments, JANA 2. And then we provide something that's again at an interface here to physics analysis. Everything in this box uses specific detector or specific data models, event data models. They're a way of encoding what the data looks like. So if I say I have a cluster and a colorimeter, then the data model says, well, a cluster has energy, it has a number of hits, it has a theta, phi, and it has an intrinsic theta and phi for the shape of it has a number of different fields. That's what a cluster looks like. Every cluster has all of those fields. If it has more than those fields, it's not a cluster. So it allows everyone to write reconstruction algorithms that accept clusters or that produce clusters, and everyone agrees what a cluster is. Then we can mix and match them the way we want, as long as we agree on the interfaces. For the geometry, we use a tool called DD4HEP, which is a geometry definition language. Why do we need that? Because why would we not define our geometry entirely in Jan4? Someone who is familiar with geometry definitions in Jan4? Some of you are. So any idea why that would not be the way we would go here? So we need geometry in 2 places. We need it to do the simulations, but then we also need it in the reconstruction. We need to know where our detectors were placed. We need to know, we need to know what the geometry of our detectors was. How many wires are there? How many strips are there on the silicon detectors? And it's hard to read that information or to get that information from Jan4. So that's why having an additional layer that defines the geometry and then in a consistent way provides it to Jan4 and provides it to the reconstruction is a way to solve that problem of having duplicated information. Yep.
Why not just develop Jan4 better? I guess better is not the word for that, but
Jan4 has a task, and it's simulation of particles in matter. As a collaboration, they are very focused on that task because they're the best software out there for that purpose. Diverting from that by, for example, becoming a service for reconstruction is not something they want to do, because it would make their main goal worse. It's all about a choice between, focus on what you're good, try not to get distracted by other things you could be doing. Otherwise you end up, doing both not very well. Yep.
Nice. It's like the modularity that you are talking about. Seems like
Right.
it would be hard to make the interfaces in between the modules though.
It's where there's a lot of thought that has to go into it. Yeah, and conscious thought, and we have to get people on both sides on board with that, right? So that's exactly why, for example, we're giving these talks. It's to make sure that we kind of, you know, are able to convey what the motivation is. Why are we doing this? Why is this important? It's because, and you know, some of you might be familiar with software that has been written for a long time, has been used for a long time, and has gotten things kind of attached to it, hacked onto it. It's not as standard. You don't necessarily know how something's going to behave or what value is going to be in some field, because it's, you know, user info 1, user info 2, and then, so that's what we're trying to avoid from the start. To facilitate all of the collaborative aspects, we use GitHub and GitLab, and we talked, you know, we heard about benchmarks in the context of PDF studies. So we're also running benchmarks. Essentially, whenever you make some change to the geometry, whenever you update something in a reconstruction algorithm, it runs GIS analysis. It runs a timeline competence scattering analysis, a DVCS analysis, deep virtual competence scattering. It runs a number of different analyses and checks that you didn't screw up something. It checks that the reconstruction still reconstructs the energies of clusters in the electromagnetic calorimeter correct. It checks that things are reproducible. So this is a recent model, maybe not quite as recent. I think it's maybe like a month or two of the date, but a model of encoded geometry in DD4HEP. So this is this abstraction layer for defining the geometry. It provides this to a number of different geometry consumers. And here's another reason why this modularity helps and why we wouldn't want this in Jan 4. This doesn't just do geometry. It does things like alignment. One of the things that we don't have to worry about right now is, you know, in our simulations, the detectors are all positioned in the right place because they're simulations. At some point, when we start building things, they're not going to be in the right place. They're going to be millimeters off in one direction, other direction. We have to figure out what those millimeter offsets are through a process of figuring out the alignment. That is something that can be done in this framework that would again add complexity to a Jan 4 implementation that they might not want to do. We can do things like importing, exporting to CAD models to compare with engineering. We can use what are called conditions databases. So for run 23511, we had this detector enabled. For the next run, we didn't, things like that. So we can provide that. So there's a lot more that is involved in this geometry definition that is taken care of by this DD4HEP component. Now, one of the things that's nice, and you'll see this in the other components as well, is that DD4HEP is not something that we wrote for EIC. It's not even something we wrote. It's a high energy physics tool. It was written for the International Linear Collider community. It's written for other high energy physics experiments, but it is a community-owned, community-supported piece of software. There's many different experiments that are using it, not just EIC, but we're all working together on developing this into what we need. Similar with this event data model. We actually, if I go back to the very first slides I was showing, in 2016, we tried to come up with a data model that defines what a cluster, what a hit, what a track looks like, and we failed. We failed multiple times because everyone in the EIC community is like, no, you know, we need this part in a track as well, or a cluster also needs to have that particular value. Or if we define a jet, it also needs to have the jettiness, or it needs to have, I don't know anything about jet, but it needs to have certain values. And we just could never agree. Sometimes it's easy to have something on the outside to point to and say, look, that community has already agreed on something. Let's use that. It's the best thing we have. And we can extend it with a little bit of things that we think might be useful for us. But nothing should rely on those extensions. It should work with the basic EDM for HEPT, event data model for high energy physics. So that includes things like, raw hits, digitized hits, tracks, vertices, clusters, particle identification. We've added to that with, in particular, detectors that are specific to EIC. Rich detectors, Dirk detectors, which you've heard about, all of these optical photon generating detectors, which are not common in most of the high energy physics experiments. So that's what we are adding to this data model and helping this data model become more complete for high energy physics and nuclear physics experiments. And once again, you see here how this data model is essentially the interface between each of the steps in our reconstruction, simulation and reconstruction chain. So the other component that is new is a streaming readout reconstruction framework. So here we are using a project called JANA 2, second version, which is used by GlueX for their streaming readouts, or for is used by GlueX and is adapted for streaming readout. They're actually an elegant approach. Every algorithm needs some input and needs some output, or produces some output. When it gets a request for something, because some other algorithm that depends on it asks for that input, then it will check, have I already calculated this? If so, I'm going to give you what I already calculated. If I haven't, well, now I'm going to do the work to calculate this. It's possible that while I need to calculate this, I have to request something else, then I'm going to contact another factory. If that one has it already in stock, it will give me what it already calculated. Otherwise, it's going to calculate something. Maybe it needs some input there. It's going to ask another factory. So it's essentially the way modern just-in-time manufacturing works applied to computer algorithms. All of these factories can scale. So we can have, let's say, 10 different factories that produce clusters for electromagnetic calorimeters, because that maybe takes a longer time. And maybe we only need one factory that combines everything and boxes it up in an event. So this JANA 2 allows us to schedule and orchestrate that. It also can manage things like access to GPUs to be able to run some things faster on GPU resources. Again, collaboration is important. So we store everything on central code repositories. Everything right now is based on Git. So we use GitHub for the code storage and for sort of the main place where we do our collaboration. One thing that GitHub isn't very good at is providing a computationally powerful backend where we can just run full simulation campaigns. So for that, we have a GitLab instance that runs at Argonne National Lab, but could run anywhere, that we use to do this benchmarking, to do tests on code. So every time when someone makes a change on GitHub, it automatically triggers some jobs on GitLab that then report back and tell us whether things worked or not. So for example, this kind of looks like this on GitHub. Someone pushed some change. It triggered a whole bunch of checks. You can't even read it. I can't even read it. I'm standing right next to it. But each of those takes, a few minutes, 2-3 minutes each. If we were to run them all simultaneously or linearly, sequentially, then of course it would take a long time. But because they run parallel, it finishes in about 50 minutes, which is still fairly long. Ideally, we'd get this down to 15 minutes. And the more we put in that, actually, the longer it takes. So that's what we're trying to then offload to GitLab, where we have more powerful servers that can support this. Because on GitHub, we only get 2 CPUs per job, and that doesn't run very fast. So that's kind of what it does. It triggers things on our GitLab server there. Now, again, none of this is specific to EIC. We're providing interfaces, and we're using those interfaces, and we're supporting community software. So this could be used for the second detector at EIC. We actually hope that the second detector at EIC will very, very strongly take a look at this and collaborate with us. There's nothing different about a track reconstruction algorithm in EPIC or in the second detector. It's going to be the same algorithm. In fact, our track reconstruction algorithm that we're using is the one from Atlas. So it's already being used from a different experiment. This could also be used by non-EIC experiments. So the solid experiment at Jefferson Lab is already either using this approach already or is strongly considering it in any case. So they're looking at it with interest. So finally, I think this is my last slide. Yeah. Well, before the caveats. So the community supported components are large, right? So we have this this data model, EDM for HEP, which really is part of a key for HEP project that provides an entire stack of software, which we are essentially using a very similar approach in our software stack. We're using things like an event display that's developed collaboratively in an experiment agnostic way. We're planning on using a reference implementation for a database, conditions database. All of those are things that are developed by large international groups and that we're using without having to develop it from scratch ourselves. I mentioned the Atlas track reconstruction. That's the package called ACTS. This is, again, we're getting back to the culture change. This is a little bit difficult again, because when we go to large funding agencies, big project managers at the Department of Energy, they're used to being able to go and knock on someone's door when the work doesn't get done for a particular project. No, they're used to being able to fire the person who didn't deliver on time. What do you do if that's a community supported project? You can't fire the person that doesn't even work for you. So there's not always the understanding that this actually is a benefit, that we now have working track reconstruction software that's been demonstrated in run 2 and now starting run 3 at the LHC, because we are able to use this community supported software. So that's sometimes a little bit of a challenge. Again, we have to change the culture and we have to understand why it is that the project managers are uncomfortable about that. But that's what we're working on. So those are the slides I have. So maybe I'll take a break here. Yeah, before going on to the more interactive part, which I'm going to keep not too long. Maybe like, what do you think? Another 20 minutes? Is that okay? So just to get everyone started, and then tomorrow we're really going to dive in. Any questions on the slide part? Yep.
Just a question on the use of analysis software such as Wouter and Python. I don't know if I heard you correctly, but it seems because we've been working in modular, like kind of style. So is it safe to say we concentrate on Python learning than C++?
No, yeah. I wouldn't say so. So let me go back to the overview here, maybe. Jan4, C++. EDM for HEP and Pod.io and EDM for EIC are Python. Jana2 is C++. ACTS is C++. There's a lot of components that are still written in C++. At the point when you're doing physics analysis at this interface layer, you can read whatever is coming out of reconstruction with either regular root. You can read it with Python. You can read it with Julia. You can read it with Excel. what we're going for here is allowing you a lot of freedom as to how you want to do your analysis, because we don't want to say you can't use root, or we don't want to say you can't use Python. You can use either. You can use 3 draw commands, or you can use our data frames, or you can use our intuples in a couple of months whenever they're released. So so all of that is possible. We don't want to. So modularity is almost making sure that we can do that, because all we have to do is make sure that the interface is supported in the target language or whatever that you want. And that's actually going to be, because these are large projects, that's going to be something that is an easier sell, because there's going to be a large community that's going to benefit from this. That's why, you know, I didn't have to learn any Julia to know that Julia is going to work as a language to analyze the output, because I know there's people who have written support for Julia who aren't even involved in EIC. So. Other questions? Okay, so let me go to my caveats. Just before we get started with actual software. EIC software is under development, and it's going to be under development. That's part of the agile part of the statement of principles. It's here now. We don't have to wait for 5 years for there to be a finished piece of software before we start using it. You can use it right now. It's just not the same as software that's been used in CMS, that's been used in Bell 2. Who was in Bell 2? Yeah, so it's not BASF2. It's not, there's lots of things that don't work yet because they don't necessarily need to work. You know, we don't need to have working alignment. We don't need to have all of the conditions databases figured out because we don't have any real data. It's simulations, right? So that you're going to see some gaps in what is working, what isn't working. The collaboration is only 1 year old, or maybe slightly over 1 year old. And it has required taking those 2 communities of the 2 detector proposals and merging them into one. That was something that went with less friction than I thought it was going to be, but still there was some friction. So even that 1 year, we didn't all like work in the same direction necessarily all the time. So keep it in mind. And even though we've tried to reuse as much as possible, we've tried to keep sort of, you know, duplication of work to a minimum. There is always going to be some level that stuff has to be rewritten. So even though there may be some gaps in what is currently possible, and even though you might think, well, but that works there, why can't we just use that? Sometimes there's good reasons for that. So with that, with those caveats, let's go and do some actual coding, or actual EIC work. So I'm going to start by saying that some of you may be familiar with the EIC environment and may know that we use containers a lot. We use Singularity. You're welcome to use whatever you usually use to access the EIC software environment, even though I'm going to show a different way here in the interest of making sure that everyone can access it. So if you go back to the where is it here? Oh, right, to the agenda. There is a link here, the top link on the little clippy. I'm dating myself. That says create EIC shell code space. So I want you to click on that. That's going to start essentially what's on the left side of my screen here, except you know it's stopped now. After you probably log in with your GitHub account. May take a while. I don't necessarily know how quickly this starts up the first time you run this, but it should at some point come up with a terminal window. And that terminal window is going to be, yeah, it'll look something like this. actually, it more likely will look something like this with the side panels. But I'm gonna hide these side panels because I'm just gonna use the terminal for now. For those of you who are not familiar with this, code spaces is something that GitHub provides for you to run code in. I have to say that technically it's not an entirely free feature in the sense that after you've been in this tutorial for 120 hours, it's going to ask you to pay for it. But I think we're pretty safe there. So after 120 hours, you would have to, wait until the end of the month for it to reset again. You get 120 hours every month. So the other links that are in the agenda, by the way, this EIC tutorial 1, that's gonna be, oops, I can as well close these slides here. So that's gonna be this this page. I'm gonna keep them side by side, and you can do the same if you want to copy and paste code from one to the other. So how's that working out? Starting this code spaces. Very buggy. It's a new product from GitHub. Is it buggy to the point where it's not starting up, or?
Yeah, still loading.
Yeah, I'm restarting.
It's a little. It takes a while to load because it's loading the entire EIC software environment. So it's taking about, I don't know, 8 gigabytes or so, and starting it on some GitHub server somewhere.
So how much cache does it cache to the computer or the browser?
So nothing. There's nothing. This all runs in the cloud. There's nothing that runs on this computer.
Right.
So if you get thrown to some recovery container, so then you can do as it should tell you. It will tell you to do Control-Shift-P. Control-Shift-P somewhere here.
Let me look.
I guess on a Mac it would say something else. I didn't see it what it said here, but but then it should give you instructions on how to do a rebuild of the environment, and that should should hopefully resolve things. So who is in some shell that looks like this? Who is in some command line like this? You are, yeah. If you have trouble, if like one of every 2 people has access to it, and you can sort of combine in groups of 2, that'd be great too. So let's see. Walk around. So build failed. Okay. Already failed. So it should start the recovery container there, right? Does it also say failed? It's running recovery container, and then it starts. Yeah. Okay.
I don't know.
So that's the other way. Oh, wait, yeah, no, you're actually in there. So if you,
It gave me an error.
did it?
Yeah.
Yeah, so get into the GitHub.
So I'm hoping that, by tomorrow, we all have access to this.
Oh, wait. Were you on the screen or is it?
Yeah.
So I was on this screen and then
So it will still start something, and then it's gonna give you instruction on how to rebuild it.
I was waiting to thank them.
I didn't even look at it. So Singularity is not gonna be installed inside there. So, so this is also gonna be. So I guess we're on. I think you are in
I'm
it.
sending you.
Yeah, so do this, rebuild container with Control-Shift-P. It's like. Right. So to cancel, yeah, so that's the creation log. So if you go to Terminal, where is the terminal?
Yeah, the problem that I've never used create.
Yeah. Now let me, okay, so we're gonna, bear with me. This is the way I figured I was gonna be able to avoid having all of you install Singularity or Docker. If you do have Singularity or Docker installed, you can use that too. And maybe by tomorrow that might be useful. If you have trouble, if we all have trouble running this.
Yeah.
So there's instructions here under setup, under the setup link that tell you how to install Singularity or Docker. This can be on your own laptop if you have Linux or Mac. If you are on, or you can use any other system that you have access to. So if you go to a BNL or a JLab system, you can, you will be able to use Singularity. So that's available there. So you should be able to use those systems. Or if you have another computing server that you use, you should be able to use that too. So there's, go back. So the difference will be, the difference will be in how you start the environment. So instead of going through the browser, it will have to go through EIC, through the Singularity interface. Now, because I'm on the podium computer here, I only have this option here, so I'm going to be using that one.
I was able to manage.
So if you are on a system that has Singularity, then the instructions are in the first part of this, I think, what is it, the second episode of this. So essentially, if you go to, let me see if I can increase this in font, no? So this is the command that would give you a command called EIC shell that you can run. And that will give you the exact same shell as we have it here in the browser. So does anyone have success on the browser part by now, or does it just keep?
Well, it says that it's running in recovery mode.
So once it's in recovery mode, it should give you like something about press Ctrl+Shift+P and then do rebuild.
I'm trying to rebuild it.
I don't know why Ctrl+Shift+P doesn't work on this Mac here. Probably because it's. Oh, there we go. Yeah. Ctrl+Shift+P should give you this kind of drop-down menu, and then if you type rebuild, you should get these two options: either rebuild container or full rebuild container. I would say try with the first one, and then if that doesn't work, try the second one.
Oh, yeah.
Yeah, trying to figure out how to deactivate that.
By name. So you can first try this.
Yeah, I have to see if I can spin on this.
Yeah.
Yeah, it's a relatively large download. So
No, it's.
so you got this?
I think it's recovery mode.
That's in recovery mode. Yeah.
But when I type in here, it's not showing.
Oh, right. First,
it's trying to open this one.
right.
Just individual, right? There is room, workspace.
Say that again?
For
That's
us,
how many
it-
team members.
So what happens if you type rebuild?
Yeah, it doesn't matter.
Huh. Strange. Have you pressed enter? Does it search?
No, I figured it out.
Okay. I guess, yeah.
I use a software.
Okay, I'm sorry for the difficulties here. Let's see, what are we gonna do? Has anyone gotten it to work?
Not yet.
Not yet. So I want to make sure that at least, so you got it to work, right? Yeah.
Trying to show them and again I restarted it.
Okay, I want to make sure there's no systemic problem that it's just plainly isn't gonna work for anyone. So, but, so let's try to, so by tomorrow, I would like you to go through, if this doesn't work by tomorrow, try to go through at least this setup to make sure you have access to a computer that has Singularity as a command that's available. And if you don't know right now where you would get such a computer, let me know afterwards, and we can figure that out. And then on that computer, we'll start tomorrow and we'll use the instructions here to get everyone started. But then we'll start tomorrow with everyone on that computer who has that has Singularity. Does that sound good?
Yeah.
So I am still going to try to figure out if we can fix this. So. Yep.
Maybe like a line of code that people can like check to make sure that it's working. Like, what's the sanity check here?
Here, DDSim. If you just type DDSim, it should sit there a bit, and then it should at least, well, okay, of course it ends with like error and all that. But it should print a whole lot of stuff and then print error, so. Yeah, for you it works. Okay. Does it work for you?
No, did you need to source something before that, or is it just right after?
Right off, it should give that. So I'm just trying to figure out whether someone who's not already working on the IC has gotten it to work, or whether it just works for you
I'm
because.
using this for the first time.
Right, but you're in the EIC group on GitHub, so I just want to make sure that that's not related. Yeah,
I got code space to work.
and you are in the EIC group?
Yeah.
You are, okay. Yeah, this is a lot of. Same thing. So maybe